So we move on to the construction of the solenoid bracket. We had a couple different configurations. Our original configuration was with two solenoids. One would open and close the valve, and the other would open and close the other valve. We found out that to get actual pull and a push solenoid, we have to specially make them. Most solenoids are just pull solenoids that would be involved when you involve the pull. So after we found that out, we had to get, like I said, full solenoid window, two to pull it closed and two to pull it open. So we had to do a teal design, so our solenoids will stack upon each other. So this is our final construction of the solenoid bracket. It's just, you see, these are the lighter, less powerful solenoids that are stacked. We had to put them underneath the more powerful solenoids because this corner edge of the solenoid overlapped this valve. So we had to stack them on top of each other, which is pretty much the only solution. A couple of problems with this bracket was when we designed it, and then we had to alter the design, mainly because the limitation of the machine shop and what the machine shop can and can't do. And originally it was in metric, and the machine shops here pretty much use SAE, which is standard issues, and you want to get all the decimals into proper SAE fractions instead of 0.265, it has to be 0.25 at this point. So pretty much had to readjust all the measurements after we designed it, which led to some problems with the machine shop.
This is more or less just a paint picture of pretty much what our whole system will look like. What you have is the engine running. It's the flywheel here. As the flywheel is spinning, we have a rotary encoder on it. Pretty much the encoder just tells us what degree the flywheel is at. And by changing the degree, it sends that information to the microcontroller. Well, by the changing degree and the time, we can check the time between the changes in degrees. We can show the RPMs of the engine. And then we use the degrees to tell exactly where it's at and what solenoid to the fire. We display all this to the LCD screen so we can show that the engine's running properly and then how fast it's running. Then we send that information, we use it in some codes, and depending on what profile we wanted to do, which is what the whole plan was to pick certain profiles, we would tell it at what degree specific what valve building. So we could say, like, if it was between like a certain amount of degrees that we saw it's at, we'd tell it to open the intake valve to let gas into the engine, then close it, and then once it hits other degrees, we tell it to open up the exhaust and then fire at specific points. Some of the testing we've done so far, we've done base testing on our original engine. Pretty much the goal of this was to not only show that we could show more fuel efficiency with any engine, but it would also be lighter. So we weighed the standard engine. We also put about 75 milliliters of gas into the engine when we ran it to see how long it would last for. We haven't done the testing on our regular engine yet, or the new engine, because we've not received all our parts back from the machine shop yet. We're still waiting on those. But once we do that, we're going to weigh the final engine after everything we've taken out of the engine, everything we've added. And then we're also going to put about the same amount of gas into it and see if the performance is improved. If time permits, we're going to actually try and change the cam profiles different from the stock engine and see if we can actually show maybe some more torque and even more fuel efficiency out of it.
As CJ pointed out earlier, we used a small Edgers engine. It's actually a Craftsman rebrand Thompson engine. Single cylinder, 2-valve engine. As you see here, we have it mounted on our table. It's a 4-cycle engine. In this picture, you can see the removed valve assembly. These are the push rods coming up from the camshaft. Those are our valve guides where our solenoids would be lined up. And you can just see how we've had to cut it a little bit here and modify it. This is a picture of the solenoids. We have these pictures you can see our solenoids. We have 2 of these to run the exhaust valve because it requires more power because of the pressure in the chamber. And those 2 solenoids over there are tubular design. They run our intake valve, which requires much less power. This one, actually, with the longer, skinnier shaft, is what's coupled to the valve, and the other one is the pull-up. This is a picture of our power transistor board. These here are the terminals for the solenoids. Basically, they're just a 2-wire design. We're using standard BJT transistors. This runs our I/O to our microcontroller. Here you can see the solenoids coupled in their mounts. This is the tube side on the intake side of the engine. We use a coupler, we set the gap to the required valve lift, and on this side you can see the power solenoids, and they're coupled in a similar fashion. Over there to the right, that is the rotor inflator mount. That used to be a bolt, we had it machined down. It couples to the crankshaft on the engine, and this thing right here is a 2-pole magnet that actually we have a magnetic rotary encoder. Here you can see the rotary encoder's magnet coupled to the crankshaft in the engine, and then this is the outside cover with the encoder on the engine. This is our microcontroller. It's just a Dragonfly bopper board. It's a 3-scale HC9S12.
As you can tell from all the complications we've had, our project isn't exactly where we want it to be. Mainly to do, we still don't even have all our parts back in the machine shop that we need to finish our testing. So that's really been holding us up. Right now, the main goal is to have the engine run idle at this moment. For the most part, this alternative goal is only going to happen once since the valves are so close and we did have to buy solenoids on the budget we had. They might not have enough force to run when we need to. A couple options we have is to either pretty much supercharge the solenoids and hope they can slow down the valves. And if for some reason, then we would have to switch to this and actually run a little bit slower than we want to. The other problem is, if our timing is off on the engine a little bit and our valve opens to when it shouldn't and the piston comes up, we can actually break the valve. And if that happens, we don't have enough time to get another valve or get a machine to have to work. So if for some reason things don't work out like we want them to, we're actually going to just put probably some sort of small motor up into the engine and have it spin the flywheel at the speed we want it to and still be able to show everything we're hoping to accomplish. And in conclusion, in today's automotive industry, everyone is looking towards like hybrids or electric engines. We think we should also just look at the combustion engine, trying to make it more fuel efficient instead of just completely scrapping the whole idea that's been working for hundreds of years. Camel's engines have been shown to produce more power, like low torque, more fuel efficient, and produce less pollution. And for a Camel's engine, there are other options such as hydraulics and things along that nature, but we feel that using an electronic-based system works the best because then we can finally tune the profiles to whatever we want. Any questions or comments?
I have one question. Since you're still using the camshaft to mount the magneto, you may not really have much reduction in the weight.
We will actually still, because the camshaft, where you lose most of your efficiency is the force that it takes to push the springs and the valves open on a regular engine. So the camshaft's just sitting there spinning freely. So there will be a little bit of added friction, but we'll still get our numbers, hopefully.
All right. Thank you very much.